Hello all, I'm back with another Unit 1 lesson, and this one is on topic 2 called materials, and specifically 2a is fluids and then 2b is solid materials, which I will cover in another video. In this video I will try to go over fluids. If it gets too long, I will maybe break it into 2 videos, but anyway, let's get started by defining what a fluid is. So a fluid, okay, is a substance, is any substance, okay, that can flow. Okay, it can be a liquid, or a gas. And despite the definition working only for liquids and gases, there are other materials that behave like fluids, like sand. So I'm going to write it in parentheses. So sand also behaves like a fluid. Okay, the density of a liquid is one of the most important properties, and it's useful when we work with upthrust, drag, and stuff like that. So let's go write it down. So the density of a liquid is one of its most important properties. Okay, and the definition is very popular. Density is written with the Greek word, the Greek letter rho. So mass over volume. So it's measured in kilograms per cubic meters. Okay. And just to give you an idea, internally we know that we now know. I mean, they didn't know this back in the era of Archimedes, for example. Okay. If you have, let's use a different color. So let's say that you have a material. It can be a solid material. Okay. We now know that solids and all materials consist of atoms and molecules, right? So maybe inside this cube, these little circles represent atoms, say. Okay, so this is a dense material. Okay, but there are other materials that have a lot of empty space between their molecules. So maybe they look like this internally. Okay. So this is less dense. So this is what density means. In the same volume, we have more mass, pretty much, right? So the more mass we contain in the same volume, the denser a material or a substance is, okay? So let's move on. I'm gonna spend some time, probably this page, talking about common shapes and their volumes, okay? In case you don't remember, or maybe you want to refresh your memory. So the most common objects we work with in physics, engineering, architecture, and stuff like that are the cube. Okay, a cube has a side A, so that's a cube. Its volume is A cubed. Then we have let me draw it first. I'm gonna have trouble pronouncing it, even though I'm a native Greek speaker. Okay, so this is called the parallelepiped, something like that, I think. So, okay, this is the width, this is the height. Okay, so that's the height, and this is the length. So the volume of this object is width, height, length. Okay, we multiply. Other common shapes are the cylinder. Okay, so this is a cylinder. Has a radius r and a height h. Okay, so its volume is pi r squared times height. Another common object is the sphere. Okay, hope this looks like a sphere. Okay, has a radius r, the volume of so let's write it down, cylinder here, I'm sorry, and sphere. Oops, what am I doing? The volume of a sphere is 4/3 pi r cubed. And then the last is the cone, the last I'm going to discuss about, because there are many other shapes, obviously. So the cone has a radius r, height h. Let's write cone over here. The volume of the cone is 1/2 pi r squared times height times capital H. All right, let's do an example, quick example. Okay. A cylindrical glass contains 282.6 grams of water. Okay. If R for the cylinder is 3 centimeters and the height is 10 centimeters, what is the density of water in kilograms per cubic meters? And here we assume that the water fills all the glass. Okay, so rho is mass over volume, so mass over pi r squared times height, so 282, so 282.6 times 10 to the negative 3 kilograms is the mass. And then we have pi, the radius is 3 times 10 to the negative 2 squared, or we can actually write this. So let's write 0.03, okay, and the height is 0.1, and all this is cubic centimeters. So rho is exactly 1000 kilograms per cubic meters. Okay, let me write a list of common materials and their density. So these are materials it's good to know their density. Just as a reference, I mean, it's good to have it in your mind in case you're working on something. Okay, so common materials and their density. Okay, so the density of air, which is a gas at 20 degrees Celsius, is 1.2 kilograms per cubic meters. Okay, so it's not too heavy. Now the density of water, which is a liquid at 4 degrees Celsius, is 1000 kilograms per cubic meters. Then the density of ice, okay, which is a solid at 0 degrees Celsius, it's actually 919 kilograms per cubic meters. So you see that it's lighter than water, that's why it floats. Okay, it's a property of water. It doesn't really happen in most materials, but it happens with ice. Some argue that this is the reason why we have life, because if ice was heavier than water, it would sink in the bottom of lakes and oceans. So any life that was found in lakes or the sea, I mean, billions of years ago, would freeze and die. Okay. So then the density of iron is 7,850 kilograms per cubic meter, and then the density of mercury is 13,600 kilograms per cubic meter. Okay, so in general, the rule of thumb is that for a gas, I'm going to write it like this. So gas, liquid, and then solid. So it's good to remember this order of magnitude, just in case. So the density of a gas is in general about 1 kilogram per cubic meter. Then that of a liquid is 1,000 kilograms per cubic meters. And then for a solid, it's 10 times that of the liquid. So 10,000 kilograms per cubic meters, okay? And this is just for estimation purposes, like in case you want to, in case you calculate something, for example, and you find it to have a density of 1 million kilograms per cubic meter. That's impossible. Okay, nuclear matter has a really high density, but this is not the point of this lesson, okay? So for high school physics, it's good to know that a gas has a density of 1 kilograms per cubic meter, liquid 1,000 kilograms per cubic meter, and a solid 10,000 kilograms per cubic meter. Okay, let's do one more example. So the density of air when heated at 80 degrees Celsius is 1.029 kilograms per cubic meter. What is the mass of air in a hot air balloon of radius 2 meters? So the density is mass over volume. So mass is density times volume. So 1.029, which is the density, times 4/3 pi, and then the radius cubed. Okay. And the units are kilograms per cubic meters times cubic meters. So this cancels. So the mass is 34.5 kilograms. Okay. So yeah, I mean, it's kind of heavy, but not that heavy. I mean, if you think about how large an air balloon is, this is not a lot of mass. Okay. Now, so far we have been doing definitions. Let's go talk about a force that is experienced by objects submerged into fluids. Okay, and this is familiar to all of us. I mean, from childhood, right? Everybody kind of likes swimming. I didn't. I do like it a little bit, but growing up at some point, I figured that probably, I don't know, something's wrong with my density or something, because I really have to fight hard to stay afloat. Other people just float. I don't know. Maybe I don't know how to swim. But anyway, so when you submerge something into water, which is a common experience, it experiences an upthrust, right? An upwards force. So, and the same goes for any other liquid, of course. So let's define it. Upthrust. It's the upwards force experienced by an object submerged into a fluid. And it can be a liquid or a gas. Remember, we just talked about the hot air balloon, which floats, right? Okay. Now it's time to talk about our ancient friend, mathematician Archimedes, and his famous principle. So, Archimedes' principle. Archimedes' principle gives you an estimation. It gives you the magnitude of this upthrust. Okay, what's wrong with me today? So, upthrust equals the weight of the fluid displaced. Okay, so upthrust is given by the density of the fluid times G times the volume displaced. Okay, and we are gonna box this. Okay, upthrust depends on the volume submerged and not the material. Okay, this is important. So upthrust depends on the volume of the material submerged. And I'm gonna come back to this in a moment. Let's draw the forces and talk a little bit about the kind of forces experienced by objects. Okay, let's go see what happens when we drop an object into a liquid. So we will assume no drag force. Okay, even though this is not true, but anyway, let's pretend. Okay, so let's say we have a glass of water. Okay, and we throw this object that has some volume into the liquid. Okay, so what's going to happen? Once it's okay, when it's outside the liquid, the only force it's its weight, right? But once we throw it into the liquid, okay, let's say in this position, it will still be experiencing its weight, but it will also experience an upthrust, which is, as we said, it's going to be equal to the rho of the fluid, okay, of the water in this case, times G times, did we say that? We did, yes, times the volume of this object, okay? And there are three cases. In the first case, if the weight is larger than the upthrust, the object sinks, right? And if we use Newton's second law, it says that the sum of all forces is M equals A, okay? Now, since weight is larger than upthrust, we will take the down, the direction that points down as the positive. So weight minus upthrust is ma, and we can use this to find the acceleration of this object as it sinks to the bottom of this glass. Okay. Is there anything else I want to say here? No. Okay. The other case is if the upthrust is larger than the weight. Okay. The object rises, and now Newton's second law tells us that if we take the upwards direction as the positive, it tells us that upthrust minus weight is ma. And we can use this to calculate the acceleration of this object as it floats upwards, okay? And the third case is if the upthrust is equal to the weight, okay, then the object is floating and the acceleration is 0, okay? Let me see. I'm trying to read through my notes here. You don't see them, but I do. Okay. Let's before moving, let's though say that in general, when an object moves through a liquid, it also experiences a drag force, okay, which points in the opposite direction than the motion. Okay, we're going to talk about this later, but briefly, let's say that we have an object sinking into some liquid. It will experience the force of weight, the upthrust, and since it's moving down, the drag force is going to be up, and let's call it D, okay? Now, if we have an object rising into air, for example, okay, then it will experience its weight, as always. There will be an upthrust, okay? But the drag force is now down, okay, because it's moving up. So let's draw it there, okay? Actually, the drag force, okay, I mean, if you want to be precise, the drag force is a small force, so it should be a smaller vector, than the weight. Okay, so let's draw the weight like this. Okay, now this is also wrong because the upthrust needs to be larger, right? So, okay, that's the upthrust, and maybe that's the drag force. Okay, something like that. All right, let's move on. Now, remember when I said earlier that that upthrust depends on the volume of the object more than it depends on the density of the object, okay? So what do I mean by that? Most boats, in case you don't know, are made of steel, right? So that's a really heavy object. If I throw steel into water, it's gonna submerge, right? It's gonna sink to the bottom. So how do boats float? Okay. So I'm gonna try to demonstrate, and then I'm gonna also show you a cool simulation, okay, which will hopefully help. So the question is, how can a metal float into water? Okay, so let's draw a small cube. Okay, so this is a cube of some of metal. Okay, so okay, let me gather my thoughts. Something's wrong with me today. So this metallic cube has some mass, some density, and some volume, right? But the volume is small, so when this cube is submerged, the displaced volume, the displaced volume is small. Okay, so remember that upthrust is equal to, if we submerge it into water, it's going to be the density of water times G times the displaced volume. And in this case, it's going to be smaller than M times G. And we can also use the fact that since density is mass over volume, we can write this as rho of water G times V is smaller than the density of the metal times G times V, okay, because mass is density times V. And if we delete, since the volume of the displaced water is the same as the volume of the metallic cube, we can see that we can immediately infer that this is because the density of water is less than the density of the metal. But still, how do boats float? Okay, so maybe we can take this cube. Okay, so maybe we can stretch. Okay, oops. Maybe we can stretch the cube. Okay, we can stretch and manipulate the cube so it becomes like follows. Okay, so maybe we use the same cube I showed you, but maybe we cast it in a way that looks, in a shape that looks like this. Okay, it's really thin. Okay, and now we submerge it into water and it floats. Okay, so this black material is our cube from before. Okay, so we have the same mass, same density, but V is now much larger. Okay, I mean, you can think of the volume as this is the volume. Okay, so this is the new volume. So now the density of water times G times V prime is larger than the mass of this object, which is the same as before. Okay, so this is how you make this is how you can make metals float. Okay, so, and I'm sorry, one important thing now, in general we will not write rho times V now, okay, for the mass, because we cast this cube into this shape now, so we don't write that. Okay, so is there anything else I want to say? So another way to see this is that in the new volume, okay, we have a combination of the metal, right? So the new volume is formed by a combination of the metal and then the density of air, okay? So the density, inside quotes, the density of this new object now is kind of an average between air and metal. So air is really light, okay? So that's why it now floats. So let's write this down. So now the volume of displaced water is large. So the density of water times G times V prime is larger than before. Okay, so upthrust is larger than the weight and the boat floats. Okay, so let's write one more comment. So this is how boats float. Okay, they have large areas of empty air of empty space actually is better. Okay, of empty space filled with air. Okay, which effectively reduces, in quotes, the density of the whole volume. Okay, so now it's time no, let's do one more thing before showing the simulation. So again, this was our initial cube with some density and some volume, and then we cast that cube into this shape. So this is the density of air. So average density is smaller than before. Actually, let's just write is small. And again, I remind you that the density of air is about 1 kilogram per cubic meter. The density of water is about 1,000 kilograms per cubic meter. And then the density of metal is about 10,000 kilograms per cubic meter, okay? So you kind of try to cast the metal into a very, very, very large object that will contain lots of empty air, reducing the average density, okay? And now it's time for the simulation I promised. So I will probably cut this part of the video and just start with the simulation. So see you in a bit. Okay, this is the simulation I promised. Let me play a little bit. Okay, so the idea is that they have two blocks, okay, 1A and 1B. So this one sinks and this one floats in water, okay. So let's go back. If you press the button in the bottom right, it resets the simulation, okay. So they, in the table here, they say that the block 1A has density of 2 kilograms per liter. 1 liter is, 1 liter is 10 to the minus 3 cubic meters, I think, right? So 1 liter to cubic meters. Give me a second. Yes, it's 10 to the minus 3. So 1 liter is 0.001 cubic meters. Okay. Let's show the vectors too. So I want the gravity. Okay, it doesn't work for some reason. Maybe. Okay. All right. So this floats and it displaces 4 liters of water. Okay. And why is that? Because the density is 2 kilograms per liter. So it displaces 4 liters of water because it's 4 kilograms. Okay, stupid. Okay, and but this submerges. Okay, let's change the fluid. Let's use something denser. Let's use oil. Okay, did something happen? I don't know why it misbehaves. So okay, let's do not mercury. Let's do oil. Okay. So it submerges more into oil, okay? But this submerges but slower. Okay. Now let's do something different. Let's do honey. Okay. Floats, sinks. Okay. And now let's do something extreme. Let's do mercury. Okay. You see how it actually, even the brick floats in mercury. Okay, and the reason is that mercury is one of the most dense. I think it's the denser liquid in nature. Okay, let's try to increase the mass. They still don't. They still float. Okay. Okay. All right. So they have the same mass. Let's do same volume. Okay. And this is back to the thing I was telling you that the volume plays a huge role. Okay, so let's see. It still floats. This simulation is nice. They even, yeah, okay. They make it bump off the mercury. Okay, so let's do same density. Okay, let's do seawater. Still float and gasoline. All right, so I'm gonna put this link in the description so you can play, but we will go back to the lesson. Okay, so the next topic in the agenda, I guess, is fluid motion. Okay, and let's start by saying that when a fluid floats, not floats, sorry. When a fluid flows, it experiences friction either with the pipes or the material around where it flows, sorry, either with the pipes or within layers of the fluid itself. Okay, so you can think of the liquid as having layers. Okay, so this is layer 1, 2, 3, and then there is friction between these layers. Okay, so let's start by talking about laminar flow. Okay, so laminar flow is when the particles within a fluid flow in smooth parallel layers okay, with minimal mixing and friction, with minimal mixing and friction between them. Okay, the flow is highly predictable. Okay, and it's also called streamlined flow. It occurs at low velocities. Okay, and there are no cross currents. Eddies or swirls. And you can go watch videos on YouTube with laminar flow. It looks really cool. So if we have a fluid, I guess, and these are the layers of the fluid. Laminar flow is when the particles do not have friction between them. So this one flows slow, then faster, then it's fastest in the middle, and then something like this. So this is the velocity profile, okay, of the flow. So in the middle we have the higher V, small friction. Actually, let's say low friction. Okay, low friction and parallel layers. Okay, we then have a turbulent flow. Okay, so flow is chaotic and unpredictable. Okay, fluid particles move in a disordered manner, creating swirls, eddies, and vortices. So this is if you, I mean, if you go near a river in the winter when it flows really chaotic and fast, this is when you have turbulent flow, especially when the water flows in between rocks and stuff like that, okay? So in turbulent flow, there are high velocities, okay, cross currents, eddies, etc. Okay, so if we go back and draw the flow, the fluid in our pipe, this time the particles move like this, okay? So this is what's happening. And actually this is the velocity profile. It's kind of flat, okay? And this is because velocity, let's write this down as well. So velocity averages out. Okay, due to collisions between particles. Okay, so turbulence now increases friction. Okay, so it is not ideal to have turbulence in boats, airplanes, etc. Okay. Therefore, because you don't want turbulence, a very important concept is streamlining. Okay, when boats, spacecraft, etc. are designed, they are designed so they are streamlined, meaning that they allow for laminar flow around them, not turbulent flow. Okay, so in boat, spacecraft, airplane designs, we strive to reduce turbulence and resistance to flow. So this reduces friction and drag force. Okay, so for example, if we design something that looks like this, if we submerge it into water, it will experience its weight, the upthrust, and then I'm gonna design a really, okay, this is the middle, okay, I'm gonna design a very small, we are assuming that it moves down, so the drag force is really small. But if we design an object to be like this, okay, so it will experience again its weight and the upthrust, but then the drag force is gonna be large, okay, because it's not streamlined, okay. And the best example of streamlining is fishes, I guess, right? I mean, they have the minimum resistance to drag force from water, right? And they are not designed. I mean, it was natural selection that made them like that. Okay, so next in line is viscosity. Okay, so viscosity is a measure of a fluid's resistance to flow. Okay, the coefficient of viscosity eta quantifies a fluid's viscosity. So the unit is pascals times seconds for the viscosity, okay? And if we break it down to base units, 1 Pascal is 1 Newton over square meter, and then times seconds. And then 1 Newton is not fundamental either, so we can break it into kilograms times meters over second squared, and then we have the meter squared and the seconds. So this cancels and this cancels. So kilograms, meters to the minus 1, seconds to the minus 1. Okay, and these are the base units. All right. So now viscosity, eta, okay, depends on the material and its temperature. Okay, in liquids, as T increases, the viscosity decreases because heat breaks molecular bonds. Okay, and the flow becomes easier. Think of honey or wax. When you heat them up, bonds break and they become more fluid, okay? The viscosity reduces, okay? Now in gases, as the temperature increases, the viscosity increases too, okay? Because gases have no bonds. They do, but they are weak. So heat makes molecules makes gas molecules move faster. Hence, we have more collisions. So we have more collisions and viscosity increases. Okay. The composition of a material also plays a role. So I'm going to mention this as well. So composition also plays a role. For example, basaltic lava contains less silica and flows fast with about 30 kilometers per hour, whereas rhyolic lava contains a lot of silica and flows slow. At about 1 kilometer per hour. Okay, I'm going to give you a table of fluids and their viscosity, so you have a reference. So fluid, we're going to also include the temperature and then eta in pascals times seconds. Okay, I have to erase this because it doesn't look good. Sorry. So fluid, T, and eta. Okay. So air, I'm gonna list air in 3 different temperatures. So 0, 20, and 100 degrees, okay, in Celsius. Okay. So 0.000017, lots of zeros, 0.000018 at 20 degrees, and then 0.000022 at 100 degrees. So you see how viscosity increases, but then for water, we have again 0, 20, and 100 degrees. So 0.0018 at 0 degrees, 0.0010, so reduces, and then it reduces further at 100 degrees. Okay. So let's this was viscosity. Now let's go see an application of viscosity, which is Stokes law. Okay, Stokes law. Okay, so the Stokes law describes the drag force experienced by a small spherical object moving through a fluid. So it describes the drag force experienced by a small spherical object moving through a fluid. Okay, so fluids can be liquids or gases, and the speed must be low, so we have laminar flow. Okay, now this force is given by, let's call it force of Stokes, is given by 6 pi times the radius of the sphere times the viscosity times the velocity. Okay, so I'm going to write this down. Radius of sphere, viscosity, and this is the velocity of the object. So let me see. So if we have a downwards motion inside the fluid then, so this is a fluid and we have a sphere moving down, so it will experience its weight, the upthrust, and the drag force. So in this case we will have, okay, moving down, we have to write mg minus upthrust minus drag equals ma, and if we are moving up, so this is the fluid, and for some reason this sphere moves up, it will experience its upthrust, the weight, and now the drag force will be down because it resists the motion pretty much. Okay, so moving down, we will have upthrust minus drag minus mg equals ma. Okay. And we will close this video by talking about the terminal velocity case. Okay, terminal velocity. Okay, and this is the case when the acceleration is 0. Okay, so for downward motion, if the acceleration becomes 0, then the velocity does not increase anymore. This is why it's called terminal velocity, because that's the highest you can reach. So if we go to this example, okay, actually let me try something. Can we do copy paste? So let's see, not cut, we want to copy. Okay, copy. Now how do we paste it? Okay, paste. Great. Okay, so let's use this example we have from earlier. So as we said, because it's moving down, we have oops, the pen. So we have okay, there you go. So mg minus upthrust minus drag is ma, and I guess when mg becomes, when the weight becomes equal to the upthrust plus the drag force, this becomes 0, and we get mg minus u minus d equals 0. And now we will use the fact that the mass is equal to the density of the sphere times v times the volume of the sphere times g. Okay, this becomes equal to the upthrust, which is equal to the rho of the fluid, the density of the fluid, times v of sphere again, because this is the displaced liquid, times the displaced volume, I'm sorry, times g, and then plus, I'm going to write it down here, Stokes force, 6 pi r eta and v. Okay, and this is the v we want to find because v is now terminal. Okay, so let's move to the next page. So we will have to write down some math. Density of the sphere, 4/3 pi r cubed times g is equal to the density of the fluid times 4/3 pi r cubed g plus 6 pi r eta v. Okay, now the pi goes away. Then the radius goes away and it becomes 2. Do we have any other cancellations? I think not. So the next step is that we have 4/3 r squared g times the density of the sphere, and then I bring to the left hand side the density of the fluid, becomes equal to 6 times the viscosity times the velocity, and then we make this 2, and then we make these 3, and therefore the terminal velocity becomes equal to 2/9 I'm sorry, r squared times the density of the sphere minus the density of the fluid over eta, and that's the terminal velocity. Okay, it's a little bit hard, but not difficult to derive. And then we can also have terminal velocity when we move up. Okay, so for upward motion, we still have A equals 0, and now we have the upthrust being equal to the drag plus mg, okay, and then the upthrust is equal to the density of the fluid times 4/3 pi r cubed times g, and this is equal to 6 pi r eta and v plus the density of the sphere, and then 4/3 pi r cubed, right? Yeah, g. And then we see that we pretty much get the same expression with the densities reversed. Okay, so we have r squared g, and then the density of the fluid minus the density of the sphere. So these two reverse pretty much over the viscosity. Okay, and this is for upwards motion. All right, I feel like this was a long video, but we covered everything you need to know about fluids for Unit 1. I have a feeling that the same exact curriculum is followed by friends who are watching these videos in the UK. If these videos are useful for you, please let me know in the comments. Let me know what I can improve and so on and so forth. And hopefully I'm going to see you in the next video.